I will discuss about kinetics of a particle. So I will focus on the force and acceleration, and the subtopic that I will discuss is about the Newton's second law of motion and also the Newton's law of gravitation. So just an introduction, when we say kinetics, this is a branch of dynamics that deals with the relationship between the change in motion of a body and the forces that cause this change. So previously, we discussed about kinematics that focus only on the motion of the particle, but in kinetics, we focus both in the motion of the particle and also the forces acting on the particle. So for kinetics, it is based from the Newton's second law, and we all know that Isaac Newton formulated three laws of motion. And for the second law, it states that when an unbalanced force acts on a particle, the particle will accelerate in the direction of the force with a magnitude that is proportional to the force. So from the statement, we have a force, and this force that is acting to the particle is proportional or directly proportional to the acceleration. And for the Newton's second law of motion, it can be written in mathematical form as F is equal to ma. So that's why we have the basic statement where the force is directly proportional to the acceleration, where the constant here is the mass of the particle. And if you notice, the F and the A, which are the force and the acceleration, are in boldface letters. And since this is in boldface letters, it means that these quantities are vectors. And when we say vectors, these are having both magnitude and direction. The above equation, which is referred to as the equation of motion, is one of the most important formulations in mechanics. So for the Newton's second law of motion, its validity is based solely on experimental evidence. And in 1905, Albert Einstein actually developed the theory of relativity and placed limitations on the use of Newton's second law for describing general particle motion. So through experiments, it was proven that time is not an absolute quantity as assumed by Newton, and as a result, the equation of motion fails to predict the exact behavior of a particle, especially when the particle's speed approaches the speed of light. And also other developments, like developments of the theory of quantum mechanics by Erwin Schrödinger and others, indicate further that conclusions drawn from using this equation are also invalid when particles are the size of an atom and move close to one another. But for the most part, these requirements, as mentioned, regarding particle speed and size are not encountered in engineering problems. Even though this equation of motion, which is the F is equal to ma, has limitations like the particle speed and the size, but particle speed and size are not encountered mostly in engineering problems. So there's no problem when we use this kind of equation, which is the F is equal to ma. So let us discuss about the other law postulated by Newton, which is the law of gravitational attraction. So this law is about the universality of gravity. It states that every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So as you can see here, we have two particles attracting to one another, and it is distance by letter r, which is the distance between the two particles. And Newton postulated this law governing the gravitational attraction between any two particles. So as mentioned here on the statement, the force between the two particles is directly proportional to the product of the masses of the two particles and inversely proportional to the square of the distance between their centers, which is represented by r. So stated mathematically, that would be F is equal to G times the product of their masses over the square of the distance between their centers, which is the r. So as you can see, G is the constant, and that is what we call the universal constant of gravitation. And according to experiment evidence, this is the equivalent value of the universal constant of gravitation. So for F, that would be the force of gravitation between the two particles. M1 and M2 is the mass of each of the two particles, and R is the distance between the two particles. So from the Newton's law of gravitational attraction, any two particles or bodies have mutual attractive, or what we call the gravitational force, acting between them. So in the case of a particle located at or near the surface of the Earth, the only gravitational force having any sizable magnitude is that between the Earth and the particle. So consequently, this force, which is termed as the weight, will be the only gravitational force considered in our study of mechanics. So when we say, or when we define weight, this is defined as the amount of force acting on the object, either due to gravity or to a reaction force that holds it in place. So this is actually the force with which a body is pulled toward the Earth. So from the equation of Newton's law of gravitational attraction, as we mentioned from the previous slide, we can develop an approximate expression for finding the weight W of a particle having a mass m1, which is equal to m. And if we assume the Earth to be a non-rotating sphere of constant density, because we all know that the Earth is rotating by its axis and also revolving around the sun, and having a mass of m2, which is equal to me, then if r is the distance between the Earth's center and the particle, we have the equation. So this equation is based from the Newton's law of gravitational attraction. And if we let small letter g equal to the universal constant of gravitation times the mass of the Earth over the r squared, which is equal to small letter g, yields to the simplest form of the equation of the weight. So that would be W is equal to mg. And by comparison, we can actually compare this equation to the Newton's second law of motion, which is the F is equal to ma. And we can see that g is the acceleration due to gravity. And if we compare that, if this is our equation of motion or the Newton's second law of motion, so F is the weight, mass is still the same, and the acceleration is what we call the gravity. So for most engineering calculations, G is a point on the surface of the Earth at sea level and at a latitude of 45 degrees, which is considered the standard location. So here the values, the gravity could be either 9.81 meters per second squared, which is for SI units, and 32.2 feet per second squared, which is for English, will be used for calculations. So in the SI unit or SI system, the mass of the body is specified in kilograms, and the weight must be calculated using the equation below. So for that, when we determine the weight, mass must be in kilogram. The gravity is using the value of 9.81 meter per second squared, and the weight is equal to Newton. So therefore, kilogram times the meter per second squared is equal to Newton. So as a result, a body of mass which has a value of 1 kilogram has a weight of 9.81 Newton. Consequently, in the FPS or what we call the English systems, the weight of the body is specified in pounds. So the mass is measured in slugs, a term derived from sluggish, which refers to the body's inertia. It must be calculated using the following, and the mass is equal to the slugs. The gravity is equal to the value of 32.2 feet per second squared. And if we multiply the two, the weight would be in pounds. So most likely it's not common that we use English unit here, especially in our country. The most common that we actually use is the SI unit. But nevertheless, we must know also the other units, either SI or English units. So this will be the topic about the Newton's second law of motion and Newton's law of gravitation.